Hey guys, and welcome to task 6.5. Here we go, diving right into how to convert from rectangular to polar and backwards from polar to rectangular. So let's start with what we know about polar form. And this is all based on what we've done with trig. We know that x is equivalent to our cosine theta, which makes sense because x was always the cosine in our unit circle. And when we do trigonometry, that adjacent side cosine represents our x coordinate. Y is our sine coordinate. Just like the unit circle, just like when we were doing opposite sides, y always correspond to sine. And this is actually just our formula for a circle. So if I were to rewrite this by saying r squared equals x squared plus y squared, this is just the Pythagorean theorem. Or it is the equation of a circle, which is the basis of all polar form. So these are the three things we're going to use most commonly. We're actually going to use them more on the second page than we use them on this first page. On this first page, most of what we're going to do is going to come from drawing a triangle. So let's draw a triangle. How do I convert from rectangular to polar form? Let's draw a triangle. I'm going to draw this point -1, 1 on our Cartesian coordinate. So -1, 1 is drawn in that second quadrant. And I'm going to take that point that I drew and draw a right triangle. So I know my x coordinate was -1, my y coordinate was +1. And if I draw a radius to that point, I have a right triangle. Well, when we're going into rectangular form, we're going into polar form, I want r comma theta. So from this triangle, I really just need to find the radius and the angle of rotation, specifically our angle of rotation from standard form. Well, this is just our 45, 45, 90 triangle. If each side of the triangle is 1, our hypotenuse is 1 radical 2. Or for our purposes, just radical 2. Now, if you didn't remember that 45, 45, 90 relationship, you could always do the Pythagorean theorem, 1 squared plus 1 squared equals c squared, and find that missing side. But knowing that it's a 45, 45, 90 triangle also tells me something pretty important. It tells me this is our pi/4 or 45-degree angle. Well, that's awesome because that tells me that our angle from standard position is 3 pi/4. So there we go. I have my radius. I have my theta. I can rewrite this as radical 2, 3 pi/4. That right there is my polar form. So let's recap how I did this once more. So what I did is I started by drawing that point. I drew that point in the Cartesian or the rectangular grid, -1 x value, +1 y value. I then drew a right triangle to that point, using the x coordinate and the y coordinate as my adjacent and opposite side. With that right triangle, I solved for the hypotenuse, which is our radius, and the angle, which is our theta. Okay, so what happens if we're given polar and we need to get into rectangular? Same thing, we're just gonna be graphing on the polar grid instead. So let's check out number 4. Again, I want to graph on the polar grid instead. So when I think about the polar grid, here is a radius of 1. Here is a radius of 2. I want a radius of radical 3 along this pi/6 line. This right here is our angle pi/6. So along that line, I'm going to extend out to radical 3, which is about 1.7. So there we go. That right there is radical 3 comma pi/6, an angle of pi/6 extending out to a radius of 1.7, which is radical 3. Well, just like the other one we did, just like this one right here, I'm going to draw a right triangle to that point. Only this time, I have been given the radius, radical 3, and that central angle, pi/6. So let's zoom in on that triangle a little bit. My central angle is pi/6. My radius is radical 3. In order to turn this into rectangular form, I just need to know what is the x coordinate, what is the y coordinate, what is that kind of x direction, and what is that y direction. Well, this is a special right triangle again, guys. This is our 30, 60, 90 triangle. And what have we been given? we've been given the hypotenuse. So if I remember this relationship, I know that 30 is some base number we call x. 60 degrees, that medium length side, is just multiplying that by radical 3. 90 degrees, the side opposite the hypotenuse, opposite the right angle, which is the hypotenuse, is just doubling that base number. So we've been given this 90 side. We've been given this is radical 3. So what does that mean the shortest side is? Radical 3 over 2. That means our side right here across from pi over 6 or across from our 30-degree angle is just radical 3 over 2. Sweet, that's our y-coordinate. Okay, so what is the medium length side or that middle side? Well, we're going to take that smallest side and multiply by radical 3. Radical 3 over 2 was x, or the shortest side, times radical 3, which just gives us 3 over 2. And perfect, that will be our x-coordinate. So when I write this in polar, from polar into rectangular form, I'm just considering, well, our x-coordinate is 3 over 2, and our y component is radical 3 over 2. Again, I started by drawing the point, just like in the other direction where I went from rectangular to polar. I drew a right triangle to that point. And now I'm just finding the x-coordinate and y-coordinate to represent the x and the y-coordinate, or adjacent and opposite representing x and y. Most times, you're going to be able to use a special right triangle. You're going to be able to use your unit circle. You're going to see that 30, 60, 90 relationship, or you're going to see that 45, 45, 90 relationship, especially if you're using a unit circle angle. So look for that, because I was able to find x and y and create my rectangular form. Pause the video now, try everything else on this first page, and press play or unpause the video when you're ready to try the second page. Okay, so we've converted points between rectangular and polar. Now we're going to convert equations between rectangular and polar. So I want to remind you about those facts that we know. We know that x is r cosine theta. X is always associated with the cosine. In our unit circle, r was just 1, but now that we're not using our unit circle, we're using any circle in the polar grid. R can be anything, so we need to make sure we're multiplying by r. Y is r sine theta. Again, y is always associated with the sine, but now that we're not on the unit circle, r is not just 1, r can be anything. And then also, all of polar form is based off the equation of a circle. So x squared plus y squared equals r squared. But this is technically also the Pythagorean identity, so we can rewrite this in different ways. For example, I could say that x squared equals r squared minus y squared. That's going to come in handy in some cases when I want to just get x's or just get y's. We could also write this as y squared equals r squared minus x squared. If this is looking familiar, it should look familiar. This really is just our Pythagorean identity. Think about it like cosine squared plus sine squared equals 1. Cosine squared is 1 minus sine squared. Sine squared is 1 minus cosine squared. We're going to use all of these forms to our advantage when we want to maybe like eliminate one variable or another. Okay, let's try the first one. In the first one, I don't see anything squared. So when I go to start substituting in, I want to substitute in these just basic relationships. I want to say, well, x is r cosine theta. So 3r cosine theta plus 5, well, y is r sine theta. 5r sine theta minus 2. So our first step really is to just substitute in those values that change us from rectangular to polar. Now that we've done that, our goal is to get an equation in the form of r equals blank. All the r's should be on one side, all the thetas should be on the other side. So let's isolate r. We've substituted in to get rid of our x's and y's. Now let's isolate r. I'm going to start by moving that 2 to the other side. Because when I move that 2 to the other side, I now see that both of these terms have an r in common, so I can factor that r out. So r times 3 cosine theta plus 5 sine theta equals 2. And this accomplishes another goal because it puts all my thetas together. So I can just divide both sides by this term right here and get 2 divided by 3 cosine theta plus 5 sine theta. And there we go. I have accomplished the goal. No more x's, no more y's. All the r's on one side equal to all the thetas on the other side. So it looks messy, it looks bizarre, but that is that linear equation in polar form. Let's try another. This one right here. Again, I could just substitute in this x and y the same way I did above, but because I see that I have a y squared, let's be a little bit more creative with it. Let's go ahead and substitute in r squared minus x squared instead. So this y squared is r squared minus x squared. And I really like this. I really like this because something looks perfect to me here. And I do mean the word perfect, like a perfect square trinomial. X squared plus 8x plus 16 is a perfect square trinomial. That means it perfectly factors to x plus 4 squared. And this is really nice because remember our goal is r equals blank. Our goal is r equals blank. So I can now get really close to having just r equals. In fact, I have r squared equals. So let's take the square root of both sides. And now I'm all set up for r equals. But I still have this pesky x in here. So I want you guys to finish this out. X is equivalent to r cosine theta. Substitute that in, and once again, isolate r. So you have all the r's on one side and all the thetas on the other side. Finish this one out and tell me what you get. It should be pretty simple. It's still going to be some fraction. It's still going to have a sine or cosine in it, but it should be much simpler than this combination of x's and y's or combination of r's and x's that we saw above. Take that same route on 13 too. Be creative. You have squareds there, x squareds and y squareds. So try substituting something out that allows us to isolate the r smoothly. Okay, pause the video, try to finish out 12, try 13. These are extra tricky, so definitely bring questions to class about this one. And move on when you're ready to try the last type of problem. So the last type of problem is taking us back to graphing sine and cosine. I'm going to go through graphing the initial sine and cosine pretty quickly. If you guys need a review of that, I would suggest you go back to our module 4 or maybe find another video about how to graph sine and cosine. I'm going to go through this pretty quickly because you guys were pros at it. So this 6 right here is our amplitude. This tells us that our sine curve is going to go up to 6 and down to -6. And this 2 right here is our frequency, telling us that our full circle is not going to be 360 or our full rotation is not going to be 360. It's now going to be 180. So when I graph this sine function, I'm starting right here at 0 and I'll come full circle by 180. So when I think about going through my entire circle, maybe you're thinking of the Ferris wheel, maybe you're just thinking of the rotation of sine. Halfway through, we come back to our midline. A quarter of the way through, we're up at our amplitude. So again, that's the top half of the wheel or the top half of the unit circle. And then we go through the bottom half of the wheel or the bottom half of the unit circle to complete our sine pattern. So let's copy that over. 45 degrees later, we're back at the kind of top of the wheel or our highest amplitude. 45 degrees later, we're back to our midline. 45 degrees later, we reach our bottom amplitude. And 45 degrees later, we come back to our midline. Okay, well, what does this look like on the rectangular grid. What does this look like on the rectangular grid? Let's just copy these points over. Let's copy these points over exactly as we see them. So I'm going to start right here. This is 0, 0. 0, 0. Let's plot that. Okay, let's go to that next point right there. This is an angle of 45, a radius of 6. So we're going to go to that angle of 45, which is right there, halfway between 0 and 90, and go out 1, 2, 3, 4, 5, 6. Okay, let's keep going around. Back to our midline at 90 degrees, our radius is 0. So here's 90 degrees. Essentially, we're just hitting that 0 point again. Okay, 135 is at our radius of negative 6. So here is that 135 line. It's halfway between 90 and 180. And we're going to go backwards 6. 1, 2, 3, 4, 5, 6. Let's keep it going. Back to our midline. This is now 180 degrees, 0. So we're going to hit that middle point again. And let's keep going. This is 225, positive 6. So there is that 225 line right there. 225 is exactly halfway between 180 and 270. And we're going to go out to positive 6. 1, 2, 3, 4, 5, 6. Cool. Let's keep going. You guys guessed it. We go back to our midline. 270, back at 0. So we're going to hit that 0 point once more. And let's keep going on to 315, which has an amplitude of negative 6. So here is our 315 line, again, halfway between 270 and 360. And along this kind of angle, we're going to go backwards 6. 1, 2, 3, 4, 5, 6. And hopefully this feels kind of like nice because we have hit all 4 quadrants now. So lastly, let's come full circle. Full circle, we come back to 360, 0. We're going to hit that point one last time. So let's connect these in order. And this is the tricky part. Just like our parametric, we want to connect these in order. We started at 0, 0. And we went out to an amplitude of 6 on 45. Back to 0, amplitude of negative 6 along 135. Back to 0, an amplitude of 6 along 225. Back to 0, an amplitude of negative 6 along 315. Back to 0. There you have it, guys. That is the polar form of that 6 sine 2x, which we've already known how to graph rectangular. This is called a rose curve, and we would describe it by its number of petals and its length of petals. Hopefully you see where that comes directly from the equation. If not, that's something we'll be exploring tomorrow. So try number 2 and number 3 on your own. You can check these with Desmos. Desmos does graph polar coordinates, or you can check them with a classmate or check them with me in class tomorrow. I hope you guys have some fun with this task. It is tricky, but it is doable. Bring your questions to class tomorrow.